Welcome to Jackal Mountain. Today we'll be showcasing how composite armor allows us to increase protection with less weight. Unlike homogeneous steel armor, composite armor is a sandwich of different materials, often steel, polymer, and hard ceramics. The need for this new type of armor arose during World War II as Allied tanks encountered the revolutionary shape-charged warheads of the Panzerfaust and Panzerschreck. These lightweight infantry weapons proved devastating against previously near-invincible armored vehicles, and stopgap defenses were hurriedly developed. Throughout the Cold War, this form of weaponry became increasingly deadly and proliferated in weapons like the RPG-7 and tow-guided missiles. To counter these threats, homogeneous steel armor increased to a thickness where its weight began to hinder mobility. Solving this problem became a critical focus of fighting vehicle design. By sandwiching hard layers of ceramics between layers of more ductile steel, the impressive penetration power of shape charges could be diminished at an acceptable weight. The different properties of each layer complement each other, allowing the armor to do more with less. The first experiments with this composite armor resulted in the prototype American T-95 tank that featured a glass composite layered into the armor called Insulite, and the Soviet T-64, initially using spherical ceramic inserts to disrupt shape-charge penetrators. Today, composite armor is seen on many modern military vehicles, with the most well-known example being the Chobham Armor on the M1 Abrams. Today we're going to demonstrate the armor protection to weight advantage of ceramic composites compared to homogeneous steel.
Now that we have all the background out of the way, I'm going to give you an overview of the targets we're going to use for this little demonstration. So let's bring the camera in and I'll show you what we got. Here is our array of targets for today's demonstration. They've all been cut down to the same 5" by 5" square so we can accurately measure the differences in weight between the targets. All the steel we are using is roughly the same composition of mild steel. None of it is armor grade or specifically hardened in any way. But what matters to us is consistency. Our results could be scaled up to armor grade steels and higher power projectiles, but the underlying concept wouldn't change. Let's start here with our control. This is a 9.5mm or 3/8 inch thick piece of mild steel. This is what everything will be compared against. Next, something a bit heavier, we have a 12.7mm or 1/2 inch thick piece of mild steel. Our first test of the composite armor concept will use a 6mm or 1/4 inch thick normal ceramic floor tile sandwiched between these two 3mm or 1/8 inch thick mild steel plates. Then we'll move up to an 11mm floor tile, which is substantially thicker, also sandwiched between two 3mm mild steel plates. Finally, we'll replace the ceramic tile with a piece of 6mm untempered glass. I'll be very curious to see how this does compared to the ceramic plates. There's one more target we're going to be shooting at. It consists of a 3mm steel plate, two 1/4 inch ceramic floor tiles, and a rear 3mm steel plate. I have previously and exhaustively weighed and measured all these targets and put the information into this handy chart. Here we can see how the different targets stack up against each other in our control. Very clearly, for similar thickness, there is considerable weight saving of composite armor compared to solid steel. If my hypothesis is correct, we will see the composite targets perform better than the solid steel at stopping 5.56. If you'd like to keep checking out this chart, pause the video now. Otherwise, let's get out to the range and get shooting. Here we are out at the range. We have that 3/8 inch thick mild steel 5" by 5" control plate set up at about 20 meters. We have our 16-inch barrel direct impingement PMAG adapter loaded up with 55 grain M193 5.56 ammunition, and we're going to see if we can't get a good control with which to base the rest of our evaluations on. Okay, here's our 3/8 inch thick control plate with the first round, and look at that. A complete through and through hole. So now that we know our control can be penetrated by the rounds we're shooting, let's try a 1/2 inch plate and see if we can go through that as well. Looks like it was not penetrated. It left a big bulge in the back, but that M855 round was not enough to punch through a half-inch of mild steel. Let's move on now to our composite armor target with a 3mm piece of steel, a 1/4 inch ceramic floor tile, and another 3mm piece of steel. We got a hole in the front, the ceramic tile is completely obliterated, and there's a big exit hole on the back right here. This little guy was from a missed shot where I didn't have the camera on, but this is from our test right now. I would say that was totally defeated. Let's move on to where we use a much thicker tile in place of that thin one. We have a small entry hole through the front plate. The tile is of course totally obliterated. There is a large bulge and a small exit hole on the rear of the back plate. Let's compare this with using the thin piece of ceramic. We had this large exit hole using a thin piece of ceramic, but when we scaled up the ceramic in the middle, the exit hole was much smaller. Now let's move on to our final test, which is the composite armor target using a piece of glass in the middle. Well, looks like we have a nice hole clean through the front sheet. I see a whole heck of a lot of shattered glass everywhere. Okay, and that rear sheet is not penetrated. We got a big bulge on the back, but nothing through the plate. We're going to do one final test. We're going to reuse a couple of the 3mm steel plates from previous tests, so they do have one existing bullet hole, but hopefully that won't interfere with this shot. And we're going to use 2 of those 1/4 inch ceramic floor tiles and see if this yields any different or surprising results. Of course, the front plate has this through and through hole. All the ceramic tile you can see is blasted apart, spread across the range, but that rear 3mm steel plate just has this big bulged out section, a whole bunch of ceramic dust caked on it, but it is otherwise uncompromised. So this, the 2mm steel plates with 2 1/4 inch ceramic floor tiles, stopped a 55 grain 5.56. Now that we're back from the range, my camera batteries are no longer failing due to the cold weather. Let's go over some conclusions for this little demonstration and see what we learned. The 3/8 inch thick solid steel control plate was totally penetrated by the 5.56 round that we were shooting. The 1/2 inch thick solid steel plate provided adequate protection, though it was far heavier than any of the other targets, and heavier than the control by 31%. The first composite target, with the thin piece of 1/4 inch ceramic, was not enough to stop a 5.56. When we used a thicker tile, it seemed to help a little bit by the far less catastrophic damage on the rear plate compared with the thin tile, but it still wasn't any better than the control. Using a layer of tempered glass inside our target, we were able to stop the 5.56 round at 20% less weight than the control, leaving only this large dent on the rear plate. Finally, our composite target using 2 thin tiles also stopped a 5.56. This time at 15.5% less weight than the control. And the dent that it produced was even less than that using the glass target. Compared to the solid steel control plate, both the glass composite and double ceramic composite targets weighed 15 and 20% less, yet they still stopped a bullet like the 30% heavier half-inch solid steel target.
What's happening here is all about how energy is dissipated through materials. Since steel is ductile, as it absorbs energy, it begins to deform and slow the projectile, which is good. But energy is not well translated away from the impact site, meaning projectiles are only resisted by the steel directly in line with the surface area of the impact. The more highly force is concentrated, the more likely a thickness of steel will be pushed to failure. Now, ceramics are hard yet brittle. When impacted, they reflect energy back into the projectile, deforming or shattering it. And then they absorb energy by shattering into a cone behind the impact site. This soaks up and spreads out force so that the following steel layer is impacted across a larger surface area, allowing it to deform and contain the projectile instead of failing and being penetrated. The multiple layers of composite armor take initial high-energy focused impacts and spread them into a succession of low-speed dispersed impacts, which further backing layers can more adequately resist until the projectile is stopped. However, I think you might have already noticed the limitations of using ceramic composites in armor. Sure, we're able to stop a single round for substantially less weight, but after that ceramic layer is compromised, it would cease to provide any protection. The homogeneous half-inch steel target weighs significantly more, but could absorb repeated strikes. On military vehicles, this limitation is mitigated by using an array of smaller ceramic inserts so that even if one or a few sections become compromised, many more will remain intact, ready to take the next strike. Another consideration that our test reveals is that composite armor is substantially thicker than denser homogeneous armor, with the glass and double tile targets being 38 and 100% thicker than the steel control. This can become an issue when the armor is spaced around an entire military vehicle. The increased bulk of composite armor results in armor with an increased surface area for the same internal area. This causes design challenges to avoid a net increased weight when using all-around composite armor. I hope this video has been a good demonstration of how the use of composite armor allows us to stop more with less weight. Thanks for watching.